So we're not doing any dynamics. We're only doing kinematics, one-dimensional kinematics. So dynamics would be if you introduce things like forces, but we're just doing just kinematics, just the motion. Okay, so in general, we have this position function, right? And that can go by a few different notations. You can have x of t, you can have y of t, you can have s of t, h of t, whatever. I'm going to stick with x of t for a lot of applications. So by one-dimensional motion, you should understand that the dimension actually refers to the fact that the particle or the car, whatever we're talking about, I mean, it can be moving in two dimensions. Like for instance, someone running around a circular track, that actually can be considered one-dimensional motion because the actual track is just essentially a line, right? He's not allowed to move kind of like around, like in like a thick track, right? There's only one track the person can actually follow. So, or a car in a highway, like the highway might actually, curve, but we're not really, we don't really care about the curve. X of t, for instance, would just denote how far along the highway that car is, right? So one-dimensional motion actually is pretty versatile. Whoops. Okay. Now we've talked about velocity, right? Remember when we first introduced limits? We actually, one of the what's it called? The motivations for limit, right, was actually average velocity versus instantaneous velocity, if you remember correctly. So let's actually recall what average velocity is. So average velocity. So if I do say x of a plus delta t minus x of a all over delta t, what is that? That is the average velocity over the interval a plus delta t, sorry, whoops, a comma a plus delta t. Right, notice this is just delta x over delta t. Right, the change in x over the change in t. So that gives you the average velocity. And in our motivation for limits, we then kind of motivated this. We said, well, how can you use the average velocity to get a better approximation of instantaneous velocity, right? And we discussed this, and everyone's kind of like, well, what if you make the delta t smaller, right? What if you look at a smaller time interval? And now that we actually have limits and derivatives, now you know what happens if I take the limit as delta t approaches 0. That's what we were actually talking about. You get what's called the instantaneous velocity, right? Oops. So v of t is dx dt, right? Instantaneous velocity. Or if you don't have a qualifier, if you just say velocity, it's understood to be instantaneous. Now, the only thing we're going to add to this, so hopefully you guys kind of remember that discussion about average velocity and velocity. So velocity is the rate of change, given what we just talked about dy dx and what this denotation means. This means that velocity is the rate of change of position with respect to time, right? Velocity tells you how fast the position is changing over time. So if I told you dx dt is equal to, say, 4 meters per second, right? That means at that moment, if you keep up that velocity 1 second later, you're going to be 4 meters ahead of where you are. Right, you'll move 4 meters. That's what that means. Now there's one more component to this which we did not introduce earlier, and this is the acceleration of the particle. So if we want to have a complete picture of the motion of a particle, not only do we want to talk about the velocity, how fast it's going right now, but we also want to talk about, well, is the particle speeding up? Is it slowing down? Is it changing direction, right? We want to actually know how not only is its position changing, but how is its velocity changing, right? Is it moving slower than before? Is it moving faster than before? So the acceleration is defined as it's actually the rate of change of the velocity with respect to time, right? Or since velocity is the is the rate of change of position, this would be the second derivative of position, or the first derivative of velocity, right? They're the same thing. Okay, so let's make sure we kind of understand this. So what if I told you that the acceleration of a certain particle was, say, negative 9.8 meters per second squared? And if you know some physics, you understand the significance of this number. So what does it mean to say that the acceleration of a particle is negative 9.8 meters per second squared? So that means at any moment, right? So this is saying that dv dt is equal to negative 9.8 meters per second squared, right? So this means at any given time, if you wait 1 second, that particle's velocity has decreased by 9.8 meters per second, right? Wait 1 second, particle's velocity decreases by 9.8 meters per second. That's what that means. Notice that the particle can still have a positive velocity, right? The particle can still be moving forward. In other words, its position can still be increasing, right? It can still be moving forward. Like the car, like think about a car. The car can still be moving forward, so its velocity is positive. But let's say you're slowing down, right? Because of, like, let's say there's some friction or something, right? And so let's say the car is still moving forward, but it's slowing down. So that would actually be a negative acceleration, right? The velocity is positive, it's moving forward, but because you're slowing down, the acceleration is negative, right? Because every second you spend, your velocity keeps decreasing, right? You're slowing down. So acceleration and velocity, obviously they're related. One is the derivative of the other, but they're kind of independent of each other, right? A particle can have negative acceleration and positive velocity, or negative acceleration and negative velocity, right? You can have any combination you want, okay? So any questions so far about this? I assume a lot of you have probably seen some of this, but I mean, we don't really need to know physics. There's no Newton's second law or anything in this class, so don't worry about that. We're just going to focus on the calculus. Okay, and the only other thing I forgot to put in here, just kind of squeeze this in here. So we also like to talk about the speed. So velocity can be positive or negative, right? Positive means the position is increasing. Negative means the position is decreasing. But we also have something called the speed. And that is just the absolute value of the velocity, meaning the magnitude. So for instance, the speedometer on your car technically only gives you your speed, right? It doesn't tell you which direction on the highway you're going, right? Are you going, north or are you going south? Right? The speedometer doesn't tell you that. Speedometer just tells you how fast you're going in whatever direction you're going. So this is called the speed.
Dr. G, speed could also have a negative acceleration, right? Or we don't really use that.
Well, okay, so acceleration is the derivative of velocity. It is not the derivative of speed, okay? So to say something is speeding down so to say the speed is decreasing is different from saying velocity is decreasing, right? Because acceleration is the derivative of velocity, not of speed. In fact, we are going to ask that in one of the questions. We're going to ask, where is the speed decreasing? And so we have to make a distinction between velocity and speed, okay? But just note that acceleration is only talking about the rate of change of velocity.
But won't the value of speed always equal velocity because the only difference is direction?
Yeah, but let's say something was moving backwards at a very high speed. Let's say something was moving backwards at 10 meters per second. So you might want to say, okay, its velocity is negative 10 meters per second, right? Because its position is decreasing.
Oh,
And let's say it's actually getting faster. Like let's say it's moving backwards at 10 meters per second, and then a second later it's 12 meters per second and 13. Like let's say it's moving backwards the whole time, right? So it's v equals negative 10, then it's v equals negative 12, then it's v equals negative 13, right? So in this case, the acceleration actually is negative, right? Because the velocity is decreasing. It's going to more negative numbers. But the speed is increasing, right? Because the speed here is 10, the speed here is 12, the speed here is 13. So the speed is increasing, but the velocity is decreasing. So there is a distinction between the two. Okay.
Professor, can you just redefine acceleration one more time?
So acceleration is the rate of change of velocity with respect to time. So just like velocity tells you how much the position or how fast the position is changing with respect to time, acceleration tells you how fast the velocity is changing with respect to time. So the acceleration can tell you things like, is the particle moving faster than before? Is the particle moving slower than before? Has the particle changed direction? Has the particle come to rest? Like that's what the acceleration can
So
help
that
you figure that out.
so that in that case where you had like -10, -12, -13, isn't it like increasing acceleration then because
No,
you're
that
still going
accelerates.
faster?
That would be negative acceleration because the velocity is decreasing. The velocity goes from -10 to -12 to -13. That's a decreasing set of numbers.
Okay, so you look at the number and the sign.
Well, yes, by decreasing we mean that the next number is less than the previous one, right? We had -10, that's bigger than -12, which is bigger than -13, right? These numbers are getting more negative, so the numbers are decreasing. So that's negative acceleration.
Gotcha. Okay, thank you.
So acceleration also takes into account direction because of velocity, right?
Yes, that's right.
So you could like a object could be speeding up. Let's say like something's falling like down to the earth. It could be speeding up, but its velocity is going to be negative.
That's right. In fact, that's exactly the example I had in mind, right? If you kind of just drop an object, right, the velocity of that object is negative because it's moving downward, and it's actually getting faster, right? As it drops, it moves faster, so it's getting more and more negative velocity. So the acceleration is negative, right? Because the velocity is getting more and more negative, but the speed of the object is increasing, right? Because the speed just cares about the magnitude of the velocity, not the direction. Yes.
This is a bit of a wider question, but are negative numbers smaller? Because would you then characterize like?
Well, we don't really like to say small and
smaller and smaller.
We don't like to say small and large because small and large sometimes have to do with size, and someone might be confused and think that's with the absolute value. So we just say things like -2 is less than -1. We say lesser. We don't say smaller. Okay, because
But would you say that
smaller is kind of an
if an
ambiguous.
object is falling,
Yes,
is its velocity getting smaller?
I would say you say its velocity is decreasing.
Okay.
Because again, the word small implies that you're looking at absolute value. You don't want to be ambiguous.